Right now, a silent war is being waged in the world's most advanced laboratories. On one side, the massive, building-sized clusters of traditional high-performance computing, the peak of silicon engineering. On the other, the ethereal, cryogenic cores of quantum processors. For years, we've been promised a quantum leap. But today, the theoretical debates end. We have the benchmark data, and the results are not what you expect.
Welcome to Algonexa. Today, we are conducting a deep dive data analysis into the performance gap between traditional HPC and the emerging world of quantum AI. By the end of this video, you'll understand the specific benchmarks where quantum is already winning, where classical supercomputing remains king, and exactly when the crossover point will change everything for the tech industry. Before we look at the quantum data, we have to establish our baseline, the modern supercomputer. Currently, the frontier system at Oak Ridge National Laboratory represents the pinnacle of classical computing. With an Exascale rating, it can perform over a quintillion calculations per second. We use the LINPACK benchmark to measure this performance, a standard that has defined supercomputing for decades. But as AI models grow in complexity, silicon is hitting a physical wall. The energy cost to move data through these massive clusters is becoming a bottleneck that no amount of cooling can solve.
Enter the quantum processors. Unlike classical bits, which are either 0 or 1, qubits utilize superposition and entanglement to explore multiple computational paths simultaneously. While systems like IBM's 433-qubit Osprey or Google's Sycamore have fewer units than a common smartphone, their computational density for specific algorithms is off the charts. The benchmark we look at here isn't just raw speed, it's quantum volume and algorithmic qubits, metrics that measure the actual useful work a quantum system can perform before noise takes over. Let's look at the actual data. In recent tests involving random circuit sampling, a task designed to be difficult for classical machines, Google Sycamore completed a calculation in 200 seconds that would take the world's fastest supercomputer roughly 47 years to finish. However, in general-purpose AI training, the story is different. Traditional HPC clusters, powered by thousands of H100 GPUs, still dominate in data-heavy tasks like training large language models. Quantum AI isn't ready to replace the GPU yet, but in optimization and molecular simulation, the benchmarks show that quantum is already achieving computational supremacy. A critical, often overlooked benchmark is performance per watt. A top-tier HPC cluster requires tens of megawatts of power, enough to fuel a small city. In contrast, while a quantum computer requires extreme cooling, the processor itself consumes negligible power. Our data analysis shows that for complex optimization problems, quantum systems are orders of magnitude more energy efficient. As we move toward a world of green AI, this efficiency benchmark may become the most important metric of all. The most interesting data isn't showing a winner, but a partnership. Companies like NVIDIA are already bridging the gap with platforms like CUDA-Q. The goal isn't quantum versus classical, but quantum-accelerated HPC. By offloading specific high-complexity subroutines to a quantum core, while keeping the heavy data lifting on classical GPUs, we are seeing a new performance tier emerge. This hybrid architecture is where the first trillion-dollar quantum AI companies will be built. The data is clear. Quantum isn't replacing the supercomputer, it's evolving it. But I want to hear from you. Do you think we are less than 5 years away from a quantum-integrated AI model, or is the silicon wall still too high to climb? Drop your thoughts in the comments. I respond to every technical breakdown. If you found this data dive valuable, hit the like button and subscribe to Algonexa for more deep dives into the future of high-performance computing. The race to the singularity is being run on two very different types of hardware. Whether it's silicon or qubits, the era of exponential computing is here. Thanks for watching, and I'll see you in the next analysis.